Okay, well, it's time to start. Welcome
you.
back, everyone, again. It's good to see all the faces. And thank you for those who sent through a few more questions and load sheets. I see you've been busy working at it. Apologies for not being able to get the recording sent to you from yesterday, sent today. I've been teaching all day long and I haven't had time to process it. I'll do both tonight's and yesterday's as soon as we finish. Just takes a little while to process those recordings and upload them. So what we're going to do this evening is dive back into system sizing, the calculations for system sizing. We're going to look at a bit more of the technical side of installations, including things like battery requirements. Batteries, there's a new standard for batteries that came out a couple of years ago, and it's got a lot of restriction on location where you can install a battery system. So I'm going to cover not too much of that standard, but more about the location restrictions and a little bit about understanding how a PV system works in terms of how it's derated by things like temperature. So you can understand why there's power loss and how that is part of your design calculations. And also another peek back at some of those load sheets and just some questions that might come up. Also, being the last session, I like to kind of have a lot of Q&A, so I'm really happy to take questions throughout this evening. So, you can just pipe it in. You can also type them into the chat. So I see someone's already typed some stuff in there. Let's have a look. So the chat's a good place. Someone says sound is muted. Can you hear me?
It was earlier muted, but it come back online. Glenn, that's me.
Oh, okay. You were muted or I was muted?
It must be system error on my side.
Okay, good. No one else reported.
All good now.
Oh, good. Okay, that's good. Someone asked about what site do we use to get the energy rating of appliances. So it's energyrating.gov.au. And I did have it up on the screen a little while back, and I might actually just bring it back again. I actually find this a very useful site when you're designing a system to get some real numbers from just knowing the model of a piece of equipment that's rated under the Mandatory Energy Performance Scheme, MEPS. So energyrating.gov.au. It's a joint database with New Zealand. So see if I can share this one again. Okay, you should be seeing the energy rating database website. Great, yep. And the trick is that there's this thing called suppliers login. It's not really, the login is not what you want. It's the registration database underneath it. It used to be right up the top of the page, so prominent, but now it's hidden down here a little bit. So when you click on that, this is where you can look up appliances, and it's a huge list that's being rated. So clothes dryers, clothes washers. I mean, for instance, clothes dryers have had a bit of an energy makeover, and now you can actually get condenser clothes dryers that are very efficient. Look at this one, 10 stars. Whoa. Incidentally, the star rating scheme got a big upgrade about a decade ago. We used to have just 5 stars, and then they added 2 more, so you can have up to 7 stars. And then they give a bonus thing called is it the crest or whatever, this little thing that goes on top for the even better stars. Why it's important to know this is if you're buying a second-hand fridge that's about 10 years old, it might be a 5-star fridge 10 years ago, but today it would be probably a 2 or 3-star fridge because the star rating scheme got a big upgrade. So condenser, if you're not familiar with what that means, a condenser clothes dryer actually uses the refrigeration cycle. So it condenses using a refrigeration cycle to extract moisture from the air. So it dries clothes very efficiently, and you end up with a big bucket of water rather than all going as hot, moist air into your laundry or wherever your dryer is. So yeah, very good. So very efficient. And as you can see, kilowatt hours per year, 52 uses. So presumably you're washing once a week. That's only 98 kilowatt hours for the whole year. So divide that by 365 for a daily average, or 52 for a weekly average. It's around about nearly 2 kilowatt hours for one whole load. So it's very good compared to just your regular non-condensing. So, gee, there's so many condensing ones now. It's amazing. The regular hot blowing air ones. I'm trying to find how far down we have to go to get one. My gosh, there's an incredible amount of condensers. There you go. So that's the registration database. Great place to hang around. And if you're a bit of a boffin, you can do advanced searches under all sorts of criteria. So, closed dryer type, capacity, programming type, star rating, model number, you name it. You can search for a very narrow range of products if you're trying to nail down something in particular. Cool. Well, welcome those who just joined us. I was just giving a little bit of intro about energy rating. So thanks for the question in the chat. And I'm just looking over it here. Raj is asking, so Glenn, could you also touch on the export limit from the inverter side to the grid, not the DNSP limitation, the calculation behind this? Raj, could you explain that question, please?
Glenn, typically the export limit is set by DNSP on a particular size of PV system for, let's say, residential. But there is also a calculation that the inverter can push it back into the grid. There are two calculations, and that's some of the installers have said there's a second calculation which relies what is the amount of current it can push back into the grid depending on the distance, how far the pole is. There's two calculations that are to be required.
Oh, okay. You're talking about the voltage rise calculation.
Yeah, that's right. Yes.
Okay. All right. I'll summarize that one. People sometimes are a bit surprised to discover that the grid doesn't want their solar power. It used to be that there was very few solar systems in Australia and New Zealand, and a small amount of injection from distributed energy resources. That's the technical term, DERs, things that are distributed on the grid that use energy or generate energy. Was hardly noticeable to utilities, or DNSP is the technical term, Distributed Network Service Provider. Incidentally, in New Zealand, they're called lines companies. But once the amount of PV grew, and you may have heard this already, but Australia has the highest penetration per capita of solar in the world. I'm getting a bit of distortion. Is anyone else hearing that?
Yeah, all good. No, all good.
Okay, must be just my end. So the highest penetration of solar per capita in the world, which is now creating a problem, and it has been for some years. So there's more and more restrictions on export. But one of those problems is that when you export energy to the grid, by the nature of Ohm's law, you have to have a higher potential at the source. That means the inverter has to have a higher voltage than the grid to flow energy towards it, which inevitably causes, at the point of connection to the grid, a small voltage rise. But this is compounded by all the other systems connected to that same piece of wire in the street. And so they're all pushing and the volts are going up. So one of the requirements in our grid connection standard is that you do not have more than 2% of voltage rise from the output of your inverter terminals to the point, and the technical term is point of common coupling, which basically is where the lines from your house connect to the lines company or utility. That's the point of common coupling. And that 2% is a calculation that installers and designers are required to do as part of an application process to connect. And the reason for it is partly the fact that the more voltage rise you get across that wire, the more out of specification is the voltage in your home. So it's actually protecting the customer. And it's part of the DNSP's requirement is to provide a supply voltage within a certain voltage range. And if you're self-inflicting a higher voltage on yourself, that is a problem. So hence that 2% voltage rise. It's got a lot easier to do. A lot of the application processors in different states have websites where you can enter the details. You can enter the size of the cable, the length of the cable, and it will give you a calculation for you. But it's not terribly difficult to do. But yeah, if you're over 2%, then they'll say, sorry, you can't put in that 10 kilowatt inverter, but we'll let you put a 5 kilowatt inverter in. Thanks for that, Raj.
Thanks, Glenn. No, that makes good sense, because there are a few jobs we have done recently. It has been limited by the cable size as well as the rise of voltage within. It is only going to be less than 3 kilowatts we could export, even though the inverter is a 5 kilowatt inverter.
The networks have been a little bit naughty too. They've got away with letting voltages drift up in Australia. So you'd be surprised to hear that the nominal voltage for the eastern side of Australia is 230 volts AC. But if you ever have a voltmeter stuck into your PowerPoint, you'll find it's way higher than that. It's often in the 240s, sometimes the 250s. And that's because until solar came around, they didn't really worry too much about it, because they were in control of what that voltage was. And whenever there was an increased demand, one of the solutions was, rather than replacing the poles and wires with thicker wires, would be to retap the transformer and slightly increase the voltage. And that sort of got carried away. No one was really measuring it to see what it was. I remember 10 years ago or so, when I was installing solar, you'd come across houses with no solar and 260 volts at their power point. And I remember saying to the customer, gee, your voltage is very high here. And they said, is that a problem? And I said, well, have you had any problems with the appliances failing? They said, yeah, actually, our plasma TV didn't last very long. And now LED downlights keep blowing. We have to keep buying a new one every 3 or 4 months. And come to think of it, the bedside radio doesn't work after 6 months. So they're actually having their appliances die from excessively high voltage, but they never knew. And it wasn't till we were installing solar that we discovered it, because we actually measured the voltage as you need to do to ensure that there's not a problem. So you could say that solar has become the canary in the coal mine, warning about existing high voltage on the network. And so now networks are much more aware of it and are managing it better.
But so higher supply voltage also means you consume more energy by Ohm's law, isn't it? Yes
and no. So it depends what the appliance is. Say if it's a resistive element and it's like a light bulb, or just an appliance that does a continuous amount of work, like a light bulb, you'll use more power. So if they increase the voltage by 10%, you'll use 10% more power. But if it's an appliance that has to do a certain amount of work, like a dishwasher or a clothes washer, it'll heat the water to a certain temperature. That's a certain amount of work. It doesn't actually matter what the voltage is. It'll still use the same amount of energy. It'll just get there quicker if you have a higher voltage. But yeah, overall, you are paying higher bills because of high grid voltage.
I think maybe sometimes the rise voltage come from the neighbors. They got from the earth fault or the neutral fault. They come from the neighbors, the high voltage, the voltage rise voltage from the MEN. From the neighbours. Yeah,
there's lots of technical reasons. It could be the neighbour actually has solar. That's actually pushing up the voltage in the street. So, yeah. What we've got is a very dumb grid at the moment, because it was designed around distributing energy from a centralised generation point, coal-fired power stations far away, and voltages would only drop as they went towards the loads. But now with distributed energy resources, inverters and batteries, etc., there's the generation that's coming from both directions, from the customer end and from the power station end. And so it's getting very hard to manage that. A more rich solution, and we're moving to that, sometimes called Grid 2.0, is where there is control of distributed energy resources. So we're already getting that in some states in Australia. South Australia introducing DER limitations. That means if your system is trying to export and the grid volts are high, it'll actually turn your system off or ramp it down. It may even be able to get if you have energy storage, to get your battery system to charge to help keep the grid voltage down. So yeah, they have a scheme called Flexible Exports in South Australia that is trying to balance the grid by using some smarts with combinations of inverters and batteries.
So just a follow-up question, Glenn.
Yeah.
Why would an inverter push the voltage up? I would have thought an inverter would have said, okay, I've got to produce 240 volt peak to peak. I'm happy, and then drive that out into the grid if it needs to. Why would it suddenly start ramping up higher than that?
It's basically Ohm's law. You won't get current flow if there's the same potential at either end of the wire.
Mm-hmm.
So you need a high potential at the source end for current to flow towards or in a certain direction.
And what you're saying is if the grid happens to be a little bit higher, then when you're trying to ship power out to the grid, you can't. So the inverter ramps it up to try to get that to happen.
That's right. It makes the problem worse. Yep. Yeah,
I got a question about for the Earth system. If someone lives in the bush, then they far from the substation. You got the off-grid solar to install the Earth under to the ground. Then the Earth working if far from substation to the transformer. If far for the Earth to the ground. If you put the stake to the ground, make it Earth system to the solar or to the house. That means the Earth working good if far from substation, if not on grid, or if only the standalone system too far from substation. Okay, to make Earth, if you got in the bush, far from the substation or far from the grid, they got the standalone system by itself, solar, everything. We need to install the Earth. If you put the Earth, to the ground, that's enough for the house. With the water pipe, that's enough.
Okay, I think I understand the question. So if you're not connected to the grid, how do you ensure in difficult soil conditions that you have a proper earth connection? Because in Australia and New Zealand, we have what's known as the TNCS system. Technically, we refer to it as MEN, multiple earth neutral. Whether you're on grid or off grid, we have MEN, which means that you have a bonding to massive earth, usually by an earth electrode or big copper stake, but it can also be through a long length of bare copper buried in the ground, which is more popular in New Zealand actually because of the soil types. But you have to test to make sure that between any part of the installation, you can get to that earth electrode down to less than half an ohm. So there's a test requirement to ensure that you do have a low resistance path to the main earth point. Also, that bonding, that main earth needs to be in a location where it will be receiving some moisture from the environment, like rain. So it can't be inside the building. It needs to be outside the building. I've even seen in Western Australia where the soil types are very difficult on off-grid systems. They've put it inside a tube, which they water. They water the tube to try and get a good connection to the earth. But anyway, I think we're going really kind of very deep into a particular technical area there, Habib. So I might draw you back a bit, and we'll go back to the system sizing calculations.
Thank you.
Cool. All right. And I did see that question, Raj, on VPP. I'll come back to that in a minute. So what I want to do is see if I can get this to happen. Is I've got to do two things. I've got to share my screen. Okay, and go, and then I've got to bring up recording. There it is there. All right. Okay, so you should be seeing daily load energy, whiteboard. Thumbs up. Thank you very much. Now, this for those who missed yesterday's session, we started going through the process of taking the load energy that from a customer's load sheet or installation load sheet that we're going to design a system for, and converting it into a certain amount of energy storage requirement. What we skipped over was E. E is how to size the PV system. So just to kind of refresh you, and I think I used the same numbers here as I did on that little diagram yesterday. So we we started with A, and I keep saying this, but it's true. A is the hardest part. Actually finding out what you're trying to design a system for. Even if it's for yourself and you're being really honest, as you saw, many of you found difficult loads to calculate, things like air conditioners, refrigerators, things that cycled, dishwashers, etc. And hence, I pointed you to the energyrating.gov.au website. The battery system voltage really is about product selection. So you might choose to use a certain product for various reasons. It's quality, it's cost, it's price. But to some extent, you also have to consider the consequences of voltage on how much current you're going to have to deliver. So I gave the example yesterday. If you've got a 10,000 watt load and you've got a 12 volt inverter, it's going to draw nearly 1,000 amps to provide 10 kilowatts under load, because the voltage will drop a little bit on the battery. And so that's 1,000 amps is ridiculous. So, well, it's just manageable. Actually, come to think of it, my system here, I peak at 1,400 amps, but it's a big system. So determined by product selection. C is just to acknowledge that you lose some of the energy when you go to use it. So the first loss I've put there is battery, and it's what's known as the round trip efficiency. It's energy out divided by energy in. That's the round trip efficiency. So you got out 9 kilowatt hours, but you put in 10, so it's only 90% efficient. Now that depends on the type of battery you've got. Modern lithium batteries are very efficient, the high 90s. But a lead acid battery, for instance, even when it's new, is only the high 80s, and it deteriorates with age. So, you can end up with quite poor efficiency. Some other chemistries have quite low efficiency because of their design. So you need to understand what that is. This is something you would get from the manufacturer. So the round trip efficiency expressed as a factor, and I think I put some numbers in there. There we go. So I put in this case, a 7,000 watt hour energy demand, which for a small dwelling would be reasonable for an efficient off-grid home. So 7 kilowatt hours per day of energy demand. But as you would have seen from your load sheets, it all depends on what appliances you have. It's a 52 volt battery system, and when we get to C, the load subsystem efficiencies, we express them as factors. Now, when I say the word efficiency, it's a kind of the reciprocal of efficiency is the factor out of 1. So 1 is 100% efficient, 0.95 is 95% efficient. It just helps with the maths. So 95% round trip efficiency on the battery, so we put in 0.95. Now I've put in wiring. You normally just think about wiring loss, but actually the reciprocal of that is the efficiency of your wiring system, of the energy you try to transmit through it, how much actually makes it to the other end. Our wiring rules, AS/NZS 3000, say a maximum of 5% voltage drop from the source to the remote part of a circuit. So I've put in the worst case. I've put in 5% voltage drop, which is 95% efficient, so 0.95. And in the case of inverters, battery inverters have a slightly lower efficiency than solar inverters because they've got a more difficult job to do. Generally, in the case of this one, it's a 52 volt battery. It's trying to make 240 volts, so it's doing a big voltage current transformation. Also, it tends to have a large transformer in it, so there's some transformer losses. And it's running at generally, on average, a lower power level. If you look at the load in a home, you don't have it running at full power all day long, as opposed to a solar inverter on a sunny day is running at full power for hours on end. So solar inverters often run at very efficient power levels. We calculated the amp hour demand based on those. So that was simply A divided by B divided by C gave us the amp hour demand from our battery system of 162 amp hours. And then I skipped over E. So I'm going to focus on E now. So E is how do we replace that 162 amp hours with a PV system? And the inputs are understanding what the load energy is. That's A in blue. And understanding what the solar resource is. Now that's where I brought in peak sun hours, PSH. So PSH, peak sun hours, is the amount of energy in kilowatt hours per square meter falling, in this case daily, on a surface for a particular design month. Now, I've been pretty awful here. I've picked a really low number because I live in mountainous Victoria. In wintertime, weather's pretty bad. And if I look at the solar radiation data, it might say that I get in June 2.7 peak sun hours. So why didn't I put 2.7 peak sun hours there? Because I looked it up on a table, because it wasn't an unshaded site. There was some shading. I actually had a shading factor to accommodate. Remember, yesterday we looked at, even the week before, we looked at Solar Pathfinder, how you can use it to analyze shading for a site. So I had to derate the amount of theoretical energy falling on a surface down to 1.9 peak sun hours. Incidentally, anyone who's from Northern Australia, this will just look terrible. I mean, you're looking at 5, 6, even 7 peak sun hours in parts of Northern Australia, just because closer to the equator, away from the coast, inland Australia is just awesome. And, Alice Springs, amazing amount of solar energy. Really, Australia should be the solar superpower of the world. I think really there's only a few places on the planet that get more solar energy. That would be Saudi Arabia in the middle of the Pacific Ocean, where no one lives. Well, people do, but on little islands. So we actually have a fabulous solar resource in Central Australia. That's why the sun cable's being proposed, by the way, because, good place to generate lots of energy. Anyway, that's peak sun hours. Maybe I'll just jump out of this and give a little bit more explanation about peak sun hours for a second. Okay, so, my keyboard out of the way. You should be seeing a white screen.
Yes.
Great. Okay, so peak sun hours actually aren't a technical term. They're just slang for megajoules per square meter or kilowatt hours per square meter. I'll show you how this works. So, the scientific unit is 3.6 megajoules per square meter equals, hang on, I got it wrong straight away. Oh yeah, no, I got it right, sorry. 1 kilowatt hour per square meter equals 1 peak sun hour. Okay, so megajoules are the scientific unit for energy. The joules is a watt second, so it's a whole unit, SI unit, joules. Whereas kilowatt hours is a mixture of power and time, the W for power and the H for time. But they're more commonly used in the electrical world. So we convert often from megajoules to kilowatt hours per square meter. But that's really hard to say more than 2 or 3 times, particularly after you've had a few beers. So we just shorten that to PSH. Right, so if you see PSH, it's really a shorthand for kilowatt hours per square meter. And what is that referring to? Well, it's referring to the way energy falls on a surface. And so if this is a day and this is noon here in the middle, and the sun's energy will, on a north-facing surface, let's say it's the north side of a roof, we'll have a bell curve because the sun's angle will be changing. Of course, that curve changes a bit with the season, how wide it is and how peaky it is. But there is a notional peak sun, and it's really only notional, of 1,000 watts per square meter. They call it a peak sun, but it's not a true peak. You will measure under cloud edge effects. That's where you've got a lot of bright white cloud, but the sun's shining through unimpeded, and the clouds reflect lots of light. You'll get 1,200, maybe even 1,300 watts per square meter for a short period of time. And if you're on the edge of space, where there are no clouds, it's 1,352 watts per square meter is what's known as the solar constant. Ironically, it's not constant because it varies with how far we are from the sun by about 50 watts. But anyway, 1,350 kilowatt hours, watts per square meter is kind of the tops. So there's our notionary peak sun, and the amount of energy falling on a surface is this area under this curvy shape. And so a way of quantifying that area is just to call it an equivalent of a sun being turned on at 1,000 watts for a certain number of hours. So we might say that area under the curve is equivalent to 3.5 peak sun hours. There you go. But actually it's all of that curvy area. So that's where we get it from. It's something that you can measure with meteorological equipment. That's something that's published by the Bureau of Meteorology, but the Bureau of Meteorology in Australia only publish horizontal data. That means flat, a panel lying flat on the ground. Well, it's not a panel, but a surface absolutely flat. What we tend to use is tilted solar panels, and there's no easy way of converting it. So this is where finding a resource that will give you that data on an inclined plane is really useful. Now, I used to have a tool that could generate this, and I've put quite a few of them in the Dropbox for you under solar radiation data. So there's quite a few sites where I've generated for monthly basis on every angle of inclination and azimuth. And so I better explain those two terms. If that's a compass, and that's north, and that's south, and that's east, and that's west, and you want to describe direction, a more accurate term is to talk in degrees of azimuth. So facing north, and I should point out, the convention is equator facing. So in the southern hemisphere, facing the equator, which is to the north of us, this is 0 degrees. And therefore going around clockwise, 90 degrees, 180 degrees, 270 degrees. So you'll talk about a orientation of, say, a roof based on the azimuth. So if I say it's a 45 degree azimuth roof, what direction is that? I can see some.
Between north and east, northeast.
Yep, northeast. There you go. Yeah. That's right. So that would be 45 degrees. You got it. Okay. Just beware, if you ever go to work in the northern hemisphere, everything's upside down. South is 0 degrees. I got caught out by this when I first started using solar tools. It was a German tool, and it defaulted to equator facing as south, and I couldn't work out why my designs were so terrible. Fortunately, I never installed them. I just couldn't work the numbers. How come winter's the best month and summer's the worst? There you go. The other thing that affects the solar radiation falling on a surface is inclination, and this is really simple. It's from horizontal. So there's horizontal, there's our plane of inclination, and there's our 35 degrees. So inclination. So those two things give you the key information that peak sun hour tables will be generated for.
Glenn, is the azimuth of the sun is exactly what you described earlier with the azimuth of the north? Because there's a term on the azimuth of the sunrise.
You're talking about the zenith, are you? The zenith, the highest point of the sun?
Because as the day breaks, the sun starts rising from wherever it is, the east or the northeast. And there is an angle of inclination with the respective part of the orientation that where it rises. Is that exactly the same azimuth we're talking, or?
So no, azimuth 0 degrees in the southern hemisphere is always true north.
Okay.
Yep. That's how it's used for describing planes that the sun falls on. And I think we did look up some of those tables last time. Just confirm with me. Did I show you a solar radiation table? I did. Yep. Oh, so I won't need to do that again. Sorry, because I've actually been teaching another course at the same time in New Zealand. So I'm just thinking, did I show you guys or the Kiwis? But anyway, there we go. Try and do one thing at a time. Yeah. So that's just a brief explanation of peak sun hours. So if I go back to my chart, I have to share again, sorry. There we go. And bring that up and tab that across. Right, so you should see my calculations again, A, B, C, D, E, F, G, or no G, just F. Yep, great, thanks. PV system, we were looking at E, and I said A is the load energy. PSH is the peak sun hours based on the actual surface that you're putting panels on. And PV system efficiency, and I've put a whole bunch of numbers in brackets. It's not the efficiency of the solar panel, it's the efficiency of all the components in the PV or the photovoltaic generation system. And so from left to right, I've picked a bunch of the four main ones. The losses due to temperature. Now, one of the problems with a PV system is as solar cells heat up, they lose power. And how much they lose power, I'll just jump to another slide for this one, is to do with temperature. So we have a thing called the voltage temperature or power temperature coefficient. What actually changes is voltage. The current doesn't change with temperature, or hardly, it's insignificant. It's all about voltage. And so as the cell temperature, and I should have written on this cell, I just realized, so I'll just put down here, cell temp. And remember that cells of a PV module heat up a lot more, typically 25 to 35 degrees hotter than the ambient temperature when the sun is shining on them, because they're like metal, they just heat up. So the cell temperature is, let's say it's 55 degrees, right? The test condition, so when you look at the data sheet for a panel or look at the back of a panel, it might say it's a 405 watt module, but it's tested at a cell temperature of 25 degrees Celsius. The reason for that is it's a comfortable temperature for people testing. They do it in a flash chamber, or it's basically a box that they heat up to 25 degrees, and they flash 1,000 watts per square meter onto that panel and measure the power output. They can't use fixed lighting because it would heat the panels up. They have to just flash it. So that 405 watts only occurs when the cells are at 25 degrees. Remember I said that in full sun, they'll heat up about 25 to 35 degrees, depending on how the panels are mounted. And I'll go into that in a minute. So to actually have a 405 watt panel produce 405 watts, it would probably have to be sitting around -5 degrees ambient. So just because of the amount of heating that you'll get even in a really cold place with the sun on the panel, it'll rise. So it's unlikely that you would get this in anything but sort of snow conditions. So let's say a typical day, it's ambient temperature happens to be 25 degrees, same as test conditions, but the sun's shining on the panel heats up 30 degrees, and so its cell temperature is 55. So there's a 30 degree difference between the temperature that it was tested at and the temperature it's being used at. And that's pretty much the case in Australia and New Zealand. Panels will be way hotter than ambient, hotter than their test condition. So to calculate what power loss there is, you take the temperature coefficient and you multiply it by the change in temperature, what we call the delta T from test conditions. So I should call this standard test conditions, STC for short, standard test conditions. So we've got 30 degrees of rise, multiply that by temperature coefficient, which gives us 10.2% power loss. So it's a negative figure. We're losing 10.2%. If you take 10.2% off 405 watts, you end up with 364 watt panel. So that's a factor of let's just call it 0.9. It's actually 0.898, but anyway, factor of 0.9 efficiency, because it's lost 10%. So that's where I got that first number for PV system efficiency in that table. So let's go back to that. And scroll to the end. Here we go. So that number there reflects the loss due to temperature. Now, you see it's only 5% loss, not 10, as I just did as an example. The reason for that is, in this system, I've chosen the design month to be midwinter, and midwinter in Melbourne, and it's partly shaded too, the site. So midwinter in Melbourne, the ambient temperature isn't 25 degrees, unfortunately. It's, well, at the moment here it's about 10 degrees. It's one small advantage of living in a cold place is your panels actually produce more power. So go Tasmania, Chris. They produce more power. They just love the cold, by the way. They really love it. So in this case, I've chosen winter. The ambient temperature is low, and I'm only losing 5% of my power. The next number, so I'll just raise that one. The next number is how much have I lost transmitting that power from the panel to my solar inverter or charge controller? I had to transmit it, as in connect a wire to it, and so it's lost some of the energy on that wire. And that wiring loss I'm putting down as 1%. Now, these days, with relatively high voltage strings, we often run our panels in 300, 400, 500 volts or so. There's very little loss because of the high voltage, low current. It's current that causes the losses, all the cable size with respect to the current. So 1% loss is very doable for cable. The next one over here is my solar inverter itself. So it's taking DC in and it's converting it to AC, and I'm losing a little bit of power in that process. In this case, I've put in 5% loss, which is actually quite high. These days, inverters are very efficient. Actually, I might change that around. Let me just call that something else. I'm going to call that dust and dirt, DD, because I just realized the second one is the inverter efficiency. The last one's the inverter efficiency. Dust and dirt, we're accommodating the fact that panels aren't always perfectly clean, unless you live in Tasmania, where the rain will wash them clean all the time. Maybe the snow might help too. So dust and dirt is a factor that you could just have to pull out of the air. There is no really easy way to measure it other than, well, put up a panel and see how much dust and dirt collects on average, but that's not very practical. So the guidelines that are often used is allow for 5% unless you know otherwise. It's kind of like just a best guess. If you live in a dry place where it doesn't rain very much, South Australia, for instance, you might have a higher figure for dust and dirt. So we're being really realistic here. And the last one, which I started off before, was the inverter efficiency. So the inverter or charge controller converting DC to AC, in this case, is 98% efficient. So that's a factor of 0.98. Now you take all those factors together and you come up with the overall efficiency of your PV system, right from the panel through to the output of the inverter. And that's, in this case, 83%, so 0.83. So that is, that should be an equals, not a divide. Let's have a look. Did I do that right? Oh, no, sorry, no, that's correct. I haven't actually given a sum there. Just realized I made a slight error. Not really an error, I just haven't finished writing the numbers in. So if I take 0.95 times 0.99 times 0.95 times 0.98 equals 0.875, or 87.5% overall. So all of, I'm really running out of room here, but let's do it in purple so you can see. All of this is 0.875. That's all of this summed. The last number on the end here, this one at the end here, where did that come from? It actually came from up here, right? And the reason for it, well, maybe I'll put the arrow on the other side, it came from up there, is that not only do you have to generate the energy that you use, which is the 7,000 watt hours from a rather poor solar resource in the middle of winter of 1.9 peak sun hours, you have to generate enough for the losses as well. And the losses are the load side. So the load is losing some of that power as well. So that's why that comes in at the end there. And that will size your PV system. In watts, it would be 5,100 and something watts. I've just written it shorthand 5.1 kilowatts. You'll notice I put a little P there. That little P, just get rid of that arrow. That little P at the end there is here, is just to remind yourself that when you purchase a solar panel, its power rating is a peak rating at standard test conditions. So you are purchasing 5.1 kilowatts of nameplate rated panels, but they won't actually produce that because of temperature. They'll be a little bit less. But yeah, P meaning nameplate rating or peak rating. All right, so you can see that the PV system sizing is a little bit more complicated, but still pretty straightforward. You could, to some extent, actually just use those numbers as a default, but this one is always going to change based on where you are. That's the one that changes the most, peak sun hours. But with the amount of shading that you have on the site and your latitude, all of those things, and the orientation of the panels. If they're on a roof, which direction do they face, will have a big impact on that number as well. And like I said, Northern Australia, that would be more like 5, 6 or 7, not 1.9. The last part we did was the battery sizing. We did this yesterday, and we had to decide how many days we want of backup, how many days of autonomy. So weather here in Melbourne at the moment is terrible, and so hardly any solar came in today. So we didn't really recharge our battery system. So we needed a battery system that can cope with a weather cycle. That's a good sort of target, an average weather cycle. The wording in the standard 4509.2 is a minimum of 2 if you have an auto start generator, and a minimum of 5 if you have a no auto start generator. Just given that you're more likely to forget to start it and you don't want to over discharge your battery system. But it's really your call what that day's autonomy are. For a 100% solar fraction, that means there is no generator. You might have to size that massively over for it to be guaranteed to always work. I visited a customer once. I used to do inspections for the government, and back in 2008 or 9, I think it was, there weren't many big systems out there, certainly off-grid. And so I was so used to seeing, 5 to 10 kilowatt systems off-grid, even smaller. I went to this property in northern New South Wales at Point Lookout, if you know where that is, and they had this enormous array on the hillside. It was like 50 panels, and I was going, wow. I knocked on the door. I was really excited. And I said, that's the biggest system I've ever seen. And the owner who came out the door said, oh, no, that's just for the telephone. Ours are the 6 panels on the shed roof. And I went, what? The telephone? He said, yeah, that's what Telstra put in for the telephone, because we get 3 weeks of fog here. So the good engineers at Telstra did the sums. They worked out what the worst weather cycle was and how big a PV array it would have to be under the worst solar conditions to keep the phone working. That was the days of guaranteed service. Now they just tell you, bugger off. Get a satellite dish or something. But yeah, that's a reality. So if you do have a job where it's 100% solar fraction, you have to make the decision based on the worst possible scenario to ensure uptime. Yeah, so that's the sizing. Any questions from that little explainer?
Yeah, please. Now, if we need add more battery, like if we add more battery at the stage, we need to add more panel to charge the battery. Yes. If you got add more battery, we need to add more panel.
Okay, so it used to be more critical when you had lead acid batteries that they got a proper equalization charge on a regular basis. So you need to be sure that within a weather cycle or two, let's say 1 to 2 weeks during the worst time of the year, that the battery system would get fully charged. And so you had to size your PV system to ensure that would occur. But with modern lithium batteries, which are much more tolerant of partial state of charge cycling, that means not fully recharging them as often. They still like to be balanced. They still like to have a fresh refresh charge, but it's not as critical as it was with lead acid. So I think that problem, Habib, is less than it used to be. More of a concern would be that the battery system's ability to supply current to the load is considered. So if you've got a 10 kilowatt inverter, can the battery system supply 10 kilowatts? So you might be a very efficient house and you think you need a very small battery system. Let's say you just need one 3 kilowatt hour battery, one lithium battery module. You think that's enough for me because I use 1 kilowatt hour a day. That's 3 days of autonomy. But actually, occasionally you switch on a big load and the battery can't supply enough current. So it's kind of like two things. You've got to consider what's the peak demand from the battery and what's the amount of energy that you need. Two things. Now, I saw Rob put his hand up. Rob, what was your question?
Yeah. I was just wondering about the situation where you've got multiple roof angles, for instance, an east-west arrangement with, say, half panels on east, half on west. Would you do the calculations separately for east and west and then add them, or does that not work because they're operating at different times of the day?
Okay, so yes, you would do them as separate calculations and add them together. Let me just explain this one. In fact, east and west is the new north. Yeah, it's kind of funny how things change. And it's partly because of the cost of solar being much lower than it used to be. And if I just draw this one here. So let's draw a house. This is plan view of a house here. So, and north is at the top. And let's say it's my favorite type of house, which is just two big plain surfaces, no hip roofs, no dormers. And there's north, there's east, there's west. Now, if you look at solar radiation tables, it will tell you that you'll get the most energy on a north-facing array, and there'll be an optimum tilt angle, and that'll vary with latitude. But if your house is not facing north, it doesn't actually work in your economic sense to try and tilt all the panels to north. You would be better off putting them on the two surface areas that you already have, parallel to the roof, like this. But you get another bonus with this arrangement. I don't know if I got the numbers right, but let's say they were the same. The bonus is that you've now got two generation profiles that look like this. So if I do a daily graph here, and if I say this is noon here, the east-facing panels are going to peak in the morning and tail off in the afternoon. The west-facing panels are going to peak in the afternoon and tail off later. So you've got two peaks, but it's the sum of those two areas that you've calculated the production of the east and you've calculated the production of the west, and you add them together, and so you're going to get an overall much flatter generation profile. Whereas, I'm getting a lot of lines here, I'll do it in grey. If I had a north-facing array, it would just be, oops, hang on, wrong pen. Here we go. A north-facing array, it would just have one peak in the middle of the day. And so I've exaggerated the peak, but it means that you get a lot of power in the middle of the day and less at either end of the day. East and west will give you a longer production cycle. And for an off-grid system, it tends to be the morning is when you want the energy because you've used it up overnight and you're just aching for the sun to come onto your panels. An east-facing array will get that sun first and will help you recover quicker from a dip overnight. It's actually one of the great benefits of a tracking system too, is that it will be, I've got a tracking system here. It's tilted perpendicular to the sun first thing in the morning and just gets those rays and straight away full power. Full power. It's 8:30 in the morning, middle of winter. It's great if it's sunny. Yep.
Okay, sorry. Now this one we do it in parallel or series or separate array, like my separate.
So you're talking about the electrical arrangement of this?
Yeah. You're not the wiring, to the inverter. Make it in series or parallel or separate, like two input to the inverter or one input or series input or parallel input.
Okay. All right. So hopefully I don't blow your mind with this, because most people think that if you have two separate strings of panels, a string is a series connection of panels, that you need an inverter that has two inputs. Most people kind of think this is what you should be doing, connecting input 1 to one string of panels and input 2 to the other string of panels. But you're allowed to do this. You're allowed to do this, connect them in parallel.
Parallel, okay.
But, and there's a big but, you can only do this if the number, so let's say we've got 8 panels here and 8 panels here. They have to be the same because the string voltages have to be the same.
Yes.
So let's say you can do it. The other question is it a good idea? You might think, well, actually, surely it's better to have two separately controlled arrays with two separate trackers. Surely it's going to produce more energy. But it turns out if there's no shading on either roof, it doesn't make any difference.
Okay.
Yeah, it doesn't make any in practice. And this has been proven by Fronius and SMA with test rigs just to show there's almost no difference. But it's really about that shading. As soon as you've got some shading, so you've got a tree, let's get a green tree out, here we go. You might have a tree that shades a little bit here in the afternoon. You've got a difference in voltage now, and so you will get a poorer performance overall.
Probably.
Yep.
Yeah.
So chop that tree down. We're greenies, aren't we? There we go.
Okay.
Great. Thanks for that, Habib. Any other questions?
Now, for the MPPT, okay, if they, for example, if they write there, they said 80 amps, 24 volt. That means if we times 80 times 24, we got the power, yeah, the power input for the power input, like the watt to the controller, the MPPT. Say if they said 80 amps, controller 24 volt. If you times 80 amps times 24, we got about, I think, 1980 watt. That means the MPPT only can be taken 1980 watt maximum.
Okay, I think I understand this one. Okay, so I'm drawing an MPPT, so
Yes.
maximum power point tracking charge controller.
That's right, yeah.
And it's a device that is built into inverters. It's on the front end of an inverter where your panels connect.
Or separate one, maybe separate.
But
separate.
yep,
But
I get it,
yeah.
Habib. But you can actually, in a DC coupled system, have a separate MPPT. And I'll just do a worked example in a second. But the way MPPTs, or the magic of MPPTs, is they can match different voltages. So you might have some panels here connected in series like this, right? And so we might have, let's say, 200 volts feeding into the MPPT. And let's say the panels put out 10 amps. So we've got 2 kilowatts of power coming into the MPPT. But on the other side, we've got a battery. And this battery is only a 24-volt battery, right?
Yes.
So we're outputting, I mean, it will vary a bit, but let's say it's putting out, or we'll just round the numbers off. Say it's a charged battery. It's 25 volts, right? Or it's charging. So we've got 25 volts coming out the other side. I need to use my calculator here. It's not very hard. So 2 kilowatts of input power divided by 25 volts tells me that we've got, the number you just said, 80 amps of current coming out the other side.
Yes.
So in MPPT, Australian invention, converts voltage and current to match what the battery system needs. It does one other thing, and this is actually even more important, and it applies equally to solar inverters and dedicated charge controllers, is it controls how the array works. So let me show you this one. And this was the genius of Peter Watkinson when he invented the MPPT in Queensland in 1983. So that's what's known as a current voltage curve of a solar panel. It's showing you the voltage and current over a range. It's kind of what's known as a load line. And this point is our open circuit voltage, the highest voltage. And at that point, you'll have 0 amps. So there's no current flowing. At this point, we've got a short circuit and we'll have no volts. So V0, volt 0. Those are the extremes. So either end of that, it's not going to do any useful work at all. What you want to find out is what combination of volts and amps coming from a solar panel give you the most power. And that's known as the power curve. And the power curve looks like this. And so there's a point on the power curve. Well, actually, if I draw it a bit better, hang on, probably about here. There we go. So different axis. This is power here. So this might be where we're producing 400 watts. And the point on the curve here is known as our maximum power point. It's the point where we get 400 watts. So the sum of current and voltage gives us 400 watts. It's getting a bit messy. I'll just turn those off. But that's the thing. But how do you find that point? It's not written on the back of the panels. You think it is because it actually says VMP on the back of the panel, but that's only under standard test conditions of 1,000 watts per square meter, cell temperature 25 degrees, and an air mass of 1.5, which is to do with the color of the light. In reality, that curve changes all the time. When you've got lower radiance, let's say the radiance is only half of full sun, the curve will look like this. When it's really dark, the curve will look like this. That could be a rainy day. So the curve moves around, which means the power point moves around too. The power point's moving all over the place as the irradiance changes and as the temperature changes. So it's the job of the maximum power point tracker to find that point. And it's a very simple and clever idea, a bit like, the paperclip. How do you find it? You start at one end, and let's say you start at open circuit voltage. So light hits the solar panel, the voltage goes up, but the inverter does nothing. It just watches it. And then it goes, okay, we've hit 100 volts. I reckon we should try and do some work. So it tries to draw a small amount of current. So it's drawing, it's a terrible color. Hang on, choose a better color. Tries to draw a small amount of current from the solar panel. And as it draws current, the voltage starts to drop. So it's drawing current, the voltage is dropping. And as it draws more current, the voltage drops more. And so it does a sum. It goes volts times amps equal power. Did I get more? Yes, keep going. So it's technically called perturb and observe. That means change something and see what happens. Really simple. It's just like getting a dial and just changing stuff. So it's doing this really fast, by the way. And so it's changing it. I got more power. I went to here. Oh, I got less power. Go back. Go back. I went this way. I got less power. Go back. So it's actually constantly hunting for that power point. And if you ever look at the voltage on a inverter and full sun, the DC voltage from the panels, it's never fixed. It'll just be moving around a little bit all the time. As soon as a cloud goes across it, it'll move a whole lot. So that's the beauty of maximum power point tracking. Okay, any questions? Okay, I'm going to change topic now and look a bit at batteries, which ironically is that slide that you've been looking at. So hang on, let me bring it back up again. There we go. So you can see, I think you can see, did I press the right button? Solar and batteries. Oh, thanks, Raj. I love seeing those thumbs up, everyone. It's terrible when I'm talking away thinking you can see something and you can't. So, there's some questions.
We got the Microsoft Edge was built with your production, maybe something wrong. Some Microsoft Edge was built with your productivity in mind. Why?
Right.
Maybe some picture, maybe some slide.
So is there a problem? You can't see my picture?
Yeah, we see like two picture.
You can see.
Two picture there. One coming up. Or maybe just something the Microsoft Edge was built in your.
Oh yeah, you can probably see the words PowerPoint slideshow VSBT at the top.
Yeah, because like double image.
Anyone else seeing a double image? No? I think it's just yours, Habib. No one else is seeing it.
Oh, yeah, sorry. So that's from my side. Sorry.
Oh, good.
From my side. Sorry. Yeah.
No, thanks for telling me. If it's a problem, I need to know. So obviously it's not. And I see a couple of questions there from Jason and Raj. I'll come back to those because I'm just going to start talking about batteries. So the battery standard ASN ZS 5139 came out in October 2019. It's a joint standard with New Zealand, but New Zealand has a different way of enforcing joint standards or any standards. Excuse me. They have to be referenced in the New Zealand electricity regulations. So they actually have to update the national regulations for electricity. So it's a bit of a big deal. It doesn't happen very often. And so New Zealand, this is best practice guide in New Zealand. It's not mandatory, but it's advisable. And I've been told by the New Zealand regulator, if there was an incident, they would in court they would be asking why you didn't use the best available information to prevent this from happening. So in a way, it's kind of enforced if everything goes pear-shaped. So the standard is you can buy them. By the way, it's cheaper to buy it from New Zealand. It's half the price. It's $245 Australian. The same standard in New Zealand is less than half the price. It's just a rort, really, how standards are so expensive here in Australia. In fact, in New Zealand, because there's a few Kiwis here, if you're a member of the Electrical Workers Registration Board, because it's your job, you get them for free. Gosh, it should be the same here, but it's not. There's really 4 standards that you have to consider when you're doing a battery system, whether it's on-grid or off-grid. So I should remind you that the battery standard doesn't care whether you're on-grid or off-grid. It's a battery standard. You also have to comply with the wiring rules for installation wiring. Standalone power systems, which is what we've been talking about. We've been talking about part 2, which is the design standard, but there's also an installation standard. It's pretty much made redundant because the battery standard's covered most of it now. There's not much. And there's a quasi-product standard called the Best Practice Guide, Battery Storage Equipment. That's an effort to cobble together a product standard for lithium-ion batteries because we never had one, but it's not really a proper product standard. It's just a collection of international equivalents. One of the key things about the Best Practice Guide is there are 2 main international standards that it calls up for lithium batteries. One's the IEC and one's the UL. The IEC is the international one, the UL is the American one, UL 1973. And you get some special dispensation in where you can install a battery if you comply with those. If you comply with the Best Practice Guide, you're considered to be a safer lithium installation. Because of the test standard that they have to comply with. The scope of any standard is really important to read because you might be worried that, it says you can't put a battery in a habitable room, but the scope will tell you what the exemptions are and what it covers. So the scope of this battery standard is 12 volt to 1500 volt batteries, connected to anything that modifies voltage, current, or frequency, which is what they call power conditioning equipment. Only rechargeable cells, which makes sense. No one wants to have a throwaway battery system that you only use once, and capacities from 1 to 200 kilowatt hours. So beyond that, it's kind of an engineer solution. The exclusions are important to consider if you're a critical power system like an acute care hospital substation, or it's a black start system for a substation, which is kind of another special category, then you're exempt from the standard. Really what they're saying is these are engineered sites. We don't need to go there. They've got their own methodologies. And the same is true of telecommunication sites. They've been managing batteries for decades. This standard doesn't apply. Really interestingly, it doesn't apply to electric vehicles. Now, we haven't got to the step yet, but you'll find that it's actually quite difficult to find a site to put a battery system. You may not even be able to put it in your garage, but you can park your electric car in there no trouble because it's covered by a product standard for safety for electric vehicles. So this is where we actually have a bit of a problem that we've put the cart before the horse. We never developed in time product standards for lithium-ion batteries, so we have to treat them as unknown in terms of risk. Dedicated UPS systems, a bit like the critical power supplies, they're exempt. And the last point is really important. If you happen to live in a mobile home or a caravan, you're exempt. You are allowed to put a very dangerous lithium battery under your bed in a caravan, but you can't put a safe one in your house in your lounge. I think what it's saying is that your life is worth less if you live in a caravan. No, the reason is there's actually a separate standard for transportable vehicles and structures. That's AS/NZS 3001. And I guess we just took the path of, well, that can be dealt with by that standard, which it doesn't say anything about where you can put a battery. So, yeah, if you have a transportable structure, there's some debate about what is a transportable structure. So if you're familiar with the term dongers, little work huts that are often on mine sites, they are transportable. Well, they are. They're often just dropped there, hence they're called dongers, I think. That's probably where it comes from. They dong them down. But if it's got a permanent electrical installation, so an earth electrode, an MEN, it's not really transportable. You've got to disassemble it to move it. So it's probably not transportable. But if it's something that complies with 3001, then it probably is. So there's your exemptions. This battery standard, it tries to avoid the mistake that our earlier 4086 standard, which was last published in 1992, Part 1, and 1997, Part 2, only dealt with lead acid, nickel cadmium, and nickel iron batteries. It didn't have any other chemistries that it dealt with. So what we've done in this standard is try to come up with a risk assessment strategy for any energy storage system. So, for instance, I put a picture of a molten salt battery there. Even though they've been around for a long time, they were never addressed in the old standard. So you can do a risk assessment. Are there any live parts? Well, yes, there are, the terminals. Are there any operational risks? Apart from short circuit, probably not. Is it a potential heat, fire, or explosion risk? Now, I did say molten salt, but ironically, it's one of the safest batteries. Salt isn't combustible. So, this is where you can come up with a risk assessment for a new technology and comply with the standard. I think I've already mentioned that it supersedes the old battery standard 4086, and it does include lead acid batteries like the ones in this picture. Now, I might skip over some of this sections. Here we go. I'm going to skip over a little bit. I want to just keep to some of the key information. Incidentally, I'll put a PDF of all the presentations I've shown you in the Dropbox, so you'll have a copy of them. If I skip a couple of slides, you'll still get them. I just won't have me talking over the top of them. There's a hazard classification by battery type table, and we list some chemistries, but of course it's not an exhaustive list, but these ones are defined in terms of what the hazards are. For instance, a lead acid battery, one of the oldest, best known chemistries, it gets a tick because it's an electrical hazard because it stores electricity. It's an energy hazard because it stores energy. It's a mechanical hazard because it's probably going to be heavy. So mechanical, i.e. it could fall and injure someone. When it gets to fire hazard, we've got two levels, level 1 and level 2. Level 1 is the highest, and that means it can self-ignite. Now, a lead acid battery, it's pretty hard to get it to self-ignite. It needs an external application of energy to do that. Like you'd have to set it on fire with something else. Whereas, so it's a level 2, whereas a lithium-ion battery is a level 1, and that's because due to manufacturing defects or misuse, things like internal dendrite growth can pierce the separator inside the cell, and you suddenly have an internal short circuit all by itself. Really, you didn't do anything externally to this battery, but because of manufacturer defect or misuse, i.e. over discharge and recharge, it will short circuit. A lithium battery has the 3 elements required for fire. It's got fuel, the electrolyte, lithium hexafluorophosphate typically. It's got heat from the ignition, and it's got oxygen as part of its internal components or stored inside the unit. So it actually will burn internally. You don't need to have an external source of oxygen. And that means it's considered the highest risk in terms of fire. Now, I saw a hand shoot up then. Who was that, Chris?
Yeah, that was for me. I'm just wondering whether lithium ion has a different type of battery. Is it just as dangerous? They seem to be publicising that this is a much safer
Which one?
technology. Lithium ion with an R, IRON, like lithium ion.
Yeah, I mean it's ferrous. So lithium iron or Fe from the from the periodic table. So LiFePO, lithium ferrous phosphate. So lithium ferrophosphate is a lithium ion with ION family. So it's a bit problematic, the word ion, ION versus IRON. Lithium ion is a suite of chemistries. So lithium ferrophosphate being one of them. And as you pointed out, it's often considered the safest lithium, though others would argue lithium titanate's the safest, and they can dispute that, who's the safest. But they are popular in applications like residential energy storage for that reason. But then you've got the high performance lithiums like nickel, manganese, cobalt, and nickel, cobalt, arsenic, NCA. They're also lithium ion batteries, but they're high performance in that they're more energy dense, often have higher discharge rates and charge rates, but they're kind of like thoroughbred horses. They can go fast, but their legs break so easily. So you've got to really manage them very carefully in terms of charge and discharge. You've probably seen there's been a few notable lithium fires. The big one in Geelong, near Geelong here in Victoria, that was, I think, lithium cobalt arsenate or lithium manganese cobalt. I'm not sure which chemistry it was, but it took a week to put out.
Most LG batteries are on recall now.
What's that?
Most LG batteries which are NCM.
Yep. Nickel, manganese, cobalt. Yeah. So unfortunately, LG Chem, one of the biggest manufacturers of batteries for energy storage, have had a massive recall because of failures of some of their cells. Yeah, it's been pretty embarrassing for them. But, on the good side, at least they're around, and at least they are doing a recall. They didn't just fold and disappear and leave all these exploding things sitting in people's garages. So a bit like Toyota, once again, they front up when they make a mistake and they recall and fix it. So good on them. So just going across that chart there, explosive gas hazard, definitely lead acid, because lead acid will evolve hydrogen and oxygen during charge. Whether it's sealed or flooded, you'll still get a small amount out of a sealed cell leaking out. So there is a potential for an explosive gas. Acid is a hazardous chemical in terms of, contact with your skin, particularly your eyes. And at high concentrations, there is a toxic fume hazard from the levels of hydrogen and other gases combined with the acid. So it gets ticks. That means you have to consider those risks in a design, and it'll flow through to things like what personal protective equipment you have to have on hand to install it, what signage you need to put at the site to warn people of those hazards, and it also affects the locations. So if we look at lead acid again, I know I've been talking about lithium a lot, but let's go back to lead acid for a second. It says note 2, and note 2 says it's considered fire level hazard level 2, which is it won't self-ignite, but it can burn. But if the batteries or the battery cases are V0, which is a non-combustibility standard or rating, that means that if you put a flame onto the battery case, it will go out when you take the flame off it. It won't keep burning, so it won't become fuel. It then becomes low risk. It becomes NA, not applicable, so there's no fire risk, which actually allows you to put a lead acid battery in a building containing habitable rooms if it's got non-combustible cases. That's pretty common. You just better check if you are using those. By contrast, lithium is very confusing in this standard. It says it's level 1, like the highest fire risk, but then it says note 1, if it is compliant with our best practice guide for battery storage equipment, which how do you find that out? Well, there's a public site, the Clean Energy Council have a list of all of the products that meet this requirement. They've just done a documentation check. Then it's NA, not applicable. So it goes from being the most hazardous to not applicable. Yeah, so interesting. But as you'll see, it doesn't get you a whole lot of advantage. You still got to have a fire barrier. if there's habitable room behind. So I'm just going to skip over these couple here. There's also these egress considerations that because a battery system can be a source of fire, so if it's a level 1 or any battery system, sorry, it doesn't have to be level 1, any battery system can't be installed at a location where it can prevent you exiting a building. So an exit you would think is a door, but in New South Wales, the regulators deemed it be any opening in the side of the building, including a garage. So here's a garage. So you have to have at least 1 metre of clearance in front of the battery and 900 mils from the opening of the battery. Now, when I say 1 metre in front, I mean, a garage is going to have heaps of metres in front, so you've got enough room to put a car in there, so that's okay. But you can't put that battery system right up against the door. It's kind of a little bit illogical. It makes sense when it's a small, door to a house, not a garage door, but it's all about if there is a fire, you can still escape the building. I'll skip over that one and onto suitable locations. So in summary, where can you install a battery system? Now, I'd skipped over what Section 4, 5 and 6 are because it's very specific to battery installers, what that means. But essentially, it's an escalation of risk. Section 4 is low risk, Section 5 is medium, and Section 6 is higher, sort of. Actually, Sections 4 and 5 are pretty much low risk. Section 6 is not necessarily higher, it's unknown. Section 6 is a category where you don't comply with the best practice guide, A, because you're not a lithium battery, because it only currently addresses lithium, which is a bit of a problem. It's a real problem, actually, because some of the safest batteries get stuck into Section 6. But that's how it is. And where can you put them? Well, no battery system can be installed inside a habitable room in a domestic installation. And that would be, and the list of habitable rooms is defined by the National Construction Code. Things like lounges, living rooms, bedrooms, kitchens, places that you spend extended periods of time. They're all habitable rooms. You can put them in a garage, a storeroom. You can put them in a bathroom, but you can't put them in a wet or damp location. So if you've got a bathroom with no water in it, you're okay. It's a weird kind of clause. Can you put them under the floor? Now, when I say under the floor, I don't literally mean in the dirt under your house, because that's a wet or damp location. You can't put them there. But let's say you've got an elevated floor or a 2-story building. Can you put them under the floor of a bedroom? So there's a bedroom on the first floor, there's a garage below. You can for lithium if it's a Section 4 and 5 system, but Section 6, no. That would be lead acid batteries, for instance. You can't put them under a floor of a habitable room. Inside a garage, generally not a problem, except there's a maybe on Section 6. That depends on what the case of the battery's made. In the case of lead acid, does it put it self-ignite? Sorry, not self-ignite. Does it sustain burning or not? If it doesn't sustain burning, then it's okay to put in a garage, but if it does sustain burning, you can't. And what about outside the building? No problem at all. In fact, outside the building is 300 mils from a wall. You don't have to be very far to be outside a building. It actually gives you a kind of weird thing, whereas you just eke your system 300 mils away from the house, and now it's not deemed to be outside, even though the wall's 300 mils behind it, and you don't have to put a fire barrier behind it. So there's the list of habitable rooms and those that are excluded. And that's the New Zealand Building Code has a slightly different way of stating it, but it's effectively the same as the Australian National Construction Code. So I think just to line up, to finish off this location question, the Section 4 and 5 systems, those are the ones that are listed on the Clean Energy Council's website as compliant with the best practice guide. Those are all the restrictions on top of being a Section 4 or 5 battery, which is supposed to be a safer one. You can't put them near exits, under windows that ventilate habitable rooms, next to appliances like hot water services, air conditioning. in ceiling spaces or wall cavities, on roofs that aren't deemed suitable. That's probably a loading issue. Under stairways or access walkways. This is causing a bit of grief. I've even had people say, but it's a concrete stairway. It's not going to burn. That's not the point. If a stairway is a means to exit an upper story and you've got a fire underneath it, there will be toxic fumes and heat. So that's kind of the rationale. So not under a stairway or an access walkway, and not in an escape route or evacuation route. Now, in a domestic home, you don't have labelled escape routes. So the application of this would be, how do you leave the building? You know, the front door, the back door. Those are your escape routes. So you can't put a battery system in those locations, but there is a caveat to that, unless you have a meter in front. So if you've got a wide hallway and you've got a meter that you can walk a meter away from that battery system to get around it, presumably while it's on fire, you can put it there. This really gets to the point where you've got to have a tape measure and walk around the site measuring stuff to try and find where you can put it. So inside buildings is difficult. That's why garages are very popular. They're generally pretty easy and on the side of a house. Section 6 is that category for all the systems that don't meet the best practice guide. Really, it's the same limitations with one additional one, which I've put in red, is you can't put them under the floor of habitable rooms. Like I said, that could be the ground floor of a garage with a bedroom above. Okay, I think I've covered all that. And I'm just going to skip forward to some pictures. I'm going to skip over Arc Flash. This is really technical stuff. Sorry if it feels like your life is flashing before your eyes, but it'll stop flashing in a moment. And I'm getting to some examples. Here we go. So to make it a bit more real, let's take a marketing picture from Tesla before the publication of the battery standard. And this would be how you could install a Tesla Powerwall. But once the battery standard was introduced, we had to keep 600 mils away from that sliding door because it's a habitable room. If that wall wasn't one of the fire-rated materials like brick, concrete, terracotta tile, or cement sheet, which I'm assuming it's a structural integrated panel, I think it's called, SIP. Architects will know what I'm talking about. I can't remember the name, SIP. I'd have to put up a fire barrier behind it. So that's typically cement sheeting or one of the other fire-rated materials that's listed in the standard. So if I go back a slide before, and you'll see I had to move the pot plants too, because I had to shuffle the battery a bit further over to the right. So I had to move the pot plants with Photoshop and put up a fire barrier behind it. And of course, I've got to put all the signage, so the warning signs, and it changes the whole look of that thing. So yeah, it's doesn't make customers very happy to have all these skull and crossbone signs everywhere, but it all depends on the manufacturer whether they in their safety data sheets list things as dangers like toxic fume hazards and hazardous chemicals. But let me take you to my place, and I've just walked around my house and taken a few pictures. This is a freestanding battery system, i.e. you can just plonk it anywhere and connect it. So it can be installed away from the wall. It doesn't have to hang off a wall. So because it can be 300 mils away from a wall, that means I don't need a fire barrier if there was a habitable room behind. Now, the picture just shows you there's outdoors behind, and this is a shed, so it wouldn't apply. But if there was a habitable room on the other side of that wall, I wouldn't need a fire barrier because I'm 300 mils away from it. And that kind of gives an advantage to a freestanding system. I jokingly say that it also gives the customer somewhere to store their firewood and their petrol cans, which isn't a joke because it does happen. People just go, oh, look, that's a nice place to put stuff. So that's my house. That's straw bale. No jokes about three little pigs, please. And I'm just looking down from my drone here at a battery system. So I think you can see my mouse here. There is it's an Alpha ESS system on the side of the house. I'm going to try and find a spot to put another battery system, but I want to check that if I was to do this job again, because this was installed about 5 years ago, could I put it at that location? So let's have a think about it. I've got to stay 600 mils away from a window if it ventilates a habitable room. Now that's a bathroom behind there and it's a sealed window. So it doesn't ventilate and it's not a habitable room. So I can put it there, no problem. What about on the east side of the house to the right here? Well, once again, there's a bathroom here and the window, even though it opens, it's still a bathroom. So it's not a habitable room. So I could put one here, but there's a vehicle access and it would be difficult to find, to protect it from impact from a vehicle. So not really suitable. You can see a better picture there. It's a vehicle access point. So they ruled that one out. Can I get past this battery system? Now, imagine I do actually have a fence around my house, which I don't, that would restrict my access to get past this battery system. Do I have 1 meter of clearance to escape my house in the case of a fire? Yes, I do. Plenty of room. So evacuation path, tick. This is the south side of the house, by the way. So let's see where else I can put it. What about the western end of the south side of the house? There's a whole lot of stuff there. There's equipment. You can't put a battery system within 600 mils of other appliances like hot water services, gas bottles, non-associated inverters. So these are water heating systems. They look like solar inverters, but they're dedicated to water heating. So they're non-associated with the battery system, so I can't put them near them. What about over here on the western side? Well, now I've got to consider what's behind that wall. It's a bedroom. The wall's made of straw bale. That's not a fire-rated material approved by the battery standard. It's not brick, terracotta, or tile, or cement sheeting. So I would have to have a fire barrier if I put it against that wall. I'd still have to consider that that's a window that opens, and therefore it ventilates a habitable room. So I've got to be 600 mils horizontally away, and 900 mils below is an exclusion zone. Well, that's ground level, so I'm not going to put it there. So I could probably put one here, but then I'm within 600 mils of equipment. Nah, I can't do it. I can't put a battery system here, but I could put one down here. There's a lot of empty wall space. I can be easily 600 mils from each of those windows. There's nothing above, but now I'm on the western side in full sun. And so I check with the manufacturer and it says, do not install in full sun. So I can't do that either. It's looking pretty bad. And this is a house on a rural property with no fences, and I'm struggling to find anywhere to put a battery. Geez, I've got a lot of solar panels. And what about the north side? Well, it's all windows and glazing and living areas. There's nowhere to put a battery on the north side. So I'm pretty dudded there. It looks like the only spot is where I've got one. So you can see that it is quite a challenge. I mean, I don't have an attached garage, so that would have been a good choice. So once again, I've got to consider that egress. If I did put it in that space, if I did build a shade, see, I've got a solar pergola here made of solar panels. If I extended that to shade this area so I could put a battery system here, I'd still have to consider, is there 1 meter of clearance if this was a fence, which it's not. So it's not really an evacuation path, so I should be okay. I could put it there, just got to build a shade area.
Mm-hmm.
So there you go. North, nothing to see here, all glazing. So it turns out it's quite hard. Now there's one last thing you should also consider is, apart from heat, is cold. That's my place in winter. It does snow, and one of the challenges for lithium batteries is they can discharge in cold conditions, but they are generally difficult to recharge. In fact, they won't let you recharge in cold conditions. So if the temperature is, below about 10 degrees, often a lithium battery will go into limp along. It'll charge very slowly. So 10 to 0, that sort of range is where they go into self-protection and charge very slowly. So you've got to consider that. Certainly if it's a standalone power system and it's your only battery system, it's a bit of a bummer that you can't charge it because it's sunny and cold and you can't charge your battery. There we go. Questions?
Any question I saw in your roof, they got the color for the solar, they got like, I think mono, but they got like dark and not dark, like black and gray. What difference between it's gray, mono, or dark color? Any different, make any different quality? If dark is black.
What's black? Sorry, I didn't catch what you're referring to.
The panel.
Oh, the solar panel. The solar panel. Oh, yes, yes. Okay.
Black. And then
Black panels. Yeah, I got you. So black panels, particularly with black frames, it's an aesthetic choice. People like the look of them. There's no performance advantage. In fact, there's a slight disadvantage. There's a slight heat gain from that darkness, but people like the look of them.
Only for color, but not different if dark or black or like gray. No different.
It's a very small difference. I wouldn't be too concerned about it. You can look at the data sheet. It'll tell you the temperature coefficient for the panel and the power rating, and you can make a decision from that.
The dark more take power, more affected by heat.
It's a very small factor.
By heat.
Actually, I'd say the biggest factor that's under your control is how you mount the panels. Hang on, let me just draw this, because I was going to cover this and I just realized I hadn't covered it. How you mount the panels actually has a big impact on their temperature. So if I bring my drawing pad back up again, so you should see a white screen.
Yes.
Good, thank you. So this is kind of rule of thumb. So if you've got a roof that's flat like this, and you put the panels on the roof flat like this, it's probably the easiest way to mount them on a flat roof. You're going to get approximately 35 degrees Celsius rise from ambient. They'll heat up a lot. And the reason for that is they trap air underneath them, and there's no convection. So you've got hot air trapped underneath the panels, and so they're going to be operating at the highest temperature. So if the ambient temperature is 30, they're going to be operating at 65 degrees. If you put them on a roof that's inclined, and basically inclined, more than about 5 degrees will do it, but 10 or 15 is better, and you mount the panels parallel to the roof like this, you'll get approximately 30 degrees temperature rise, because now you're getting some convection. So heat will start to go up the back and cause a small amount of convection, which gives you a 5 degrees drop in temperature, which actually will give you about 1.5% more power. So actually it's probably more significant than the color of your panel is the way you mount it. Horizontal, worse; inclined, better; and best is, here's our flat roof, putting the panels on tilts. Now we're about 25 degrees above ambient. And the reason for that is twofold. You're getting convection because of the tilt, but you're also, with wind, getting a little bit of breeze, exposure to any air movement. So they're more prone to cool. And therefore they'll run, in this case, about 3% more power than the flat roofs.
Okay.
Yeah. Now those numbers, they're not scientific. They're what they call rules of thumb from experience. I thought I'd test it because I've got thermocouples on my panels. I've got tilted ones and I've got parallel to the roof ones. I haven't got any flat. And on average, over a sunny day, these numbers actually stack up. So I'm happy to endorse them. Someone else?
When it's Ewan, what happens if we put up a cement sheet barrier and the owner paints it?
Okay, anything after you've done the installation, had it inspected, is not your problem. But if you paint it, you compromise its fire rating unless it's a fire rated paint.
Mm.
And there are such things. My house actually has fire rated paint on the outside.
Okay, thanks.
And the EARC panels by Sunman, they're actually glued onto the roof. Whether it is going to be, will that affect any of those parameters what you talked about?
I definitely think they would run hotter because there would be no convection, but I've not tested it. Yep. Remember, it's not wrong for them to be hot. It's just that you've got to accommodate greater losses. You may just compensate by putting on more panels. Once again, my adage, the answer is always more solar panels.
Yeah, then for the battery, which one? The safer one for the lithium battery, safe to install, safer because not cause heat or fire. Which one? The safety battery to use?
Which is the safest
Safer
battery
one
to use?
buy and use. Yeah, for lithium. Which one? Safe.
Oh, okay. This will be. There's lots of debate about this. So probably the two competing standard chemistries are lithium titanate and lithium ferrophosphate.
Fully phosphate. Yeah. This one the best one.
But
more safe.
there's more to safety than just the chemistry. It's how the batteries are managed, where they're installed, the design of the case. All of those things add to the safety. I mean, I like to give the example that if all cars ran on gas when we first invented the internal combustion engine, and gas requires like an airtight fitting that you connect to the vehicle and you fill your car up with LPG. And then someone came along and said, I've got a better fuel. It's called petrol. You just pour it through a hole in the side of the vehicle. You don't need any special training. Just there's a sign to say don't smoke and don't talk on your mobile phone. Do you think that would get up? Nah, it wouldn't. I'd just say it's too dangerous. But we have it because we've accommodated the risk by understanding it well and having, to some extent, some safety information around it. So when it comes to batteries, you might have essentially a chemistry that is potentially dangerous, but it's managed very well, whether it's by the BMS, the battery management system, or by the way it's encased or the way it's installed, and the location.
Then for the battery, for the lead acid battery, when it is installed inside the box we can make it from timber or metal or plastic cover.
Anything you like. There's no requirement for it to be of any particular material.
Okay, in the box, then okay.
Yeah, there's other requirements to do with restricting access to unauthorized people. So if you build a box and there's exposed terminals inside it, it's got to have a lock and padlock or some means of restricting access to it. It's got to, if it has explosive gases like lead acid, it's got to have the appropriate ventilation. And there's actually formula for that in the standard for working out the ventilation requirements. So there's some other construction considerations, but not the material of the box itself.
Oh, thank you. Yeah.
Anyone else?
One observation, Glenn. When manufacturers like LG Chem, I'm just giving an example. They make a pouch cell which is under 3 millimeters in thickness, and when you discharge a battery, and when you're discharging current, and that generates a lot of heat, and physics tells you the heat is quite damaging when the thickness is small. So in other words, if you look at a Power Plus battery, which has got a cylindrical cells, it's got a much tolerance into a temperature rise within the cell compared to a battery of a pouch cell. Is that something that has been taken by the standards?
No. In fact, we don't even differentiate the different chemistries of lithium. We just bunch them all together in the standard.
But the physics is going to be the same. The amount of energy.
Yes. It's actually an imperfect standard. It was rather rushed, if you ask me. I was on the committee that helped write it, but it was rushed. It was actually pushed by government because we had this problem. Masses of lithium batteries were being installed in homes and we had no adequate installation standards for them. So it kind of got pushed through pretty quickly. Already we're considering a new update to it. In fact, breaking the standard into two parts. So there'll be a installation standard separate from a performance standard. So, a design standard from a safety installation standard. So there'll be two parts. But anyway, that's in the future. And we will probably better address the safety risks of different chemistries as well. But anyway, we're not there yet. So we're just taking the very cautious route. In fact, we probably have the harshest regulations in the world when it comes to installing batteries. I don't know if you've seen any of the marketing from European companies. It's often a battery in the lounge next to the lounge suite. Yeah, wouldn't happen here. Now we've only got about 15 minutes left. I'm just wanting to see if anyone's got a side question, something we've not covered well enough, or a different area that I can explain?
Okay, sorry. Now for the efficiency, does the power output divide the input? The power output divide input, or input divide the output?
Okay, the lesser divided by the greater. So
Lesser.
yeah. So the output, due to entropy, you don't get more than you started with. So there's losses. So if you get 9 kilowatt hours out of a battery, but you put 10 in, 9 divided by 10 will tell you the efficiency.
Okay.
Yeah, you got to times it by 100 to get percent, but that's just maths. Yep.
Okay. The output divide the input.
Oh, I can see some questions I haven't answered. Sorry, I better go over to the chat. I did promise to do this, and way back there was a question from Raj about VPP. Where's that gone? There it is. Could you touch on VPP, virtual power plants? Virtual power plants are where you, when I say you, a energy retailer aggregates lots of systems together and can control them. Well, they offer the control usually to someone who needs that service, like AEMO, the Australian Energy Market Operator, or maybe even the DNSP, the lines company or utility, who need that control. If you think about it, when you start getting hundreds and thousands of battery systems being connected to the grid with inverters, and the fact that many of them have the smarts to be connected through the cloud to be controlled, i.e. charge now or discharge now, you have a virtual battery, a big virtual battery. And it's proving to be very useful as a way of balancing the variabilities on the grid. And so offering what's known as frequency control and ancillary services, or FCAS for short. So virtual power plants are something that quite a few of the states are getting excited by. South Australia was the first. We've got them coming into Victoria and I think New South Wales, where retailers will offer you an incentive to be part of a VPP. And that will be that you get to allow them to control your inverter battery system occasionally within certain parameters. You'll get recompense in terms of your electricity rate. So you make money providing that service.
Is it actually, Glenn, is it more beneficial to use the stored energy for yourself rather than subscribing to a VPP?
It's questionable. I think the jury's still out on the economics of it, because we need to see over time how it works. It may be that you're providing most of the service and getting not much compensation for it. So you may not want, and also might lock you into a particular retailer, who might not have very attractive electricity plans. So that's probably the bigger downside. Incidentally, I don't know if you know this, but there's a thing called the loyalty tax in Australia, which means if you're loyal to your electricity company, you'll be done over, because they offer you a cheap rate to churn to them, and after 1 year, you go back to the basic rate. So that's loyalty for you. You're better to keep churning as often as you can. Question from Jason. How do you size the inverter? May I ask only the coincidental power demand or maximum power? Jason, I think I've covered that already. Maybe you might not have been here yesterday. We looked at VA demand and surge demand. Those are the key points. So you might want to go back and have a look at the recording when I upload that tomorrow. But we did cover that. Ewan asked, what if we install cement sheet barrier? Oh, and the owner paints it. We've answered that one. And someone says they had to go. Yeah. Cool. All right. I think I've covered all the questions. All right. Anyone else? Someone who hasn't had a chance to ask a question, please pipe up.
Yeah, I did ask a question there. If you can, I sent a question there. I sent one question.
Hang on, Habib. I think someone who hasn't had a question.
Yeah, that's me. I sent one.
Oh, you sent one. Right. Okay. You've got a 12 volt, 250 amp hour times 4.
Battery, full battery. This one, lead acid battery. Lead acid.
Yep. how many PV panels need to charge the battery? Well, this comes down to how you're going to use that battery. So it's not enough information. If that's a system that's a backup system, you probably need one panel because it's just going to sit there on float for its whole life. If you're going to fully discharge it and then recharge it in one day, you're going to have to size the PV based on 1 day of autonomy. The equations that we just did, that would be 1 day of autonomy. But if you're going to discharge it and then recharge it over several days, discharge it over several days and recharge it over several days, then based on the days of autonomy you put into that formula will determine the size of your combination of that battery capacity and your load energy demand will determine the size of your PV. So the answer actually is in that formula.
Oh, thank you. Okay.
Okay, someone else. Oh, I can see the boardroom. Looks impressive.
Okay, now my question: what difference between the hybrid inverter and the off-grid inverter, off-grid and hybrid?
All right.
What difference between both?
I'm going to do a little drawing. I did plan to do this, so here we go. Move my keyboard out the way. So you can see my hand?
Yes, thanks.
Oh, good. Okay. Tea. So let's take a hybrid inverter. Now, I actually prepared one before. Here we go. It's a hybrid inverter. It's an Alpha ESS. Actually, it's the one on the back of my house. You just saw it in that picture. Okay, so Alpha ESS, and this particular model is the Smile 5. Now, what makes it a hybrid inverter? A hybrid inverter can have the grid connected to it. It can have solar panels connected to it. It can have some loads connected to it. And it can have some loads on, it can have some loads which are on the grid side. I'm putting those there. And some loads which are essential. Now, this is not always the case. Not all hybrid inverters have essential power, but it's pretty common these days. So let's draw the lines here. AC power is blue, so we're bringing in grid power. We are supplying through a dedicated backup circuit our essential loads. So we'll call those essential power supply, EPS. So these are the loads that will be backed up if the grid fails. Then we'll have our PV connected to it. Now this is a dual MPPT, so we can have two different types of panels. So we've got some 405s and some 455s, two strings connected by DC. So that's the DC cables here. And we've got some loads which are on the grid side. I'll make a bit more room for those over here. We've got some loads which are on the grid side, which aren't backed up if the grid fails. But they are being supported in the sense that there's an energy meter. It's a bit big. See if I can find a little energy meter. I haven't got a little one. But I'll put it there. We have an energy meter that sits between the grid and everything else. And that energy meter is supplied by the Alpha ESS system. And so that energy meter is going to communicate with the Alpha system about what's happening. How much energy are we sucking from the grid? So I might actually stick the grid right up there. And so we can draw one more line. So it's looking at the energy flowing from the grid. Is it flowing to or from the grid? And if it sees energy flowing from the grid, and it's because your grid-only loads, you say a hot water service or a heat pump or something like that, consuming power, it will try to displace the grid power by supplying energy to those loads at a rate to stop you drawing in from the grid. But if there's a grid outage and we lose the grid, we lose these will go off, but this keeps working. And this is where a big plus comes in. A hybrid inverter that is internally DC coupled. That means its internal batteries, which are these 2 battery modules at the bottom here, they're 10 kilowatt hours each, are charged from these solar panels even when the grid's not there. So without the grid, we still are getting solar power, charging our battery, and we're supplying our essential circuits. And best of all, from an installation point of view, it's all in one thing. It's an all-in-one solution in this case. You can have hybrid systems that have separate battery and hybrid inverter, but the offer is all-in-one. Habib, did that answer your question?
Yeah, thank you. Because I got disconnected for 1 minute. Disconnected.
Well, lucky that the recording's there, so you can catch that later on. But yeah, hybrids is so-called hybrid because actually it's just a marketing term. Are very popular because of that function of being able to supply energy to all of the loads, irrespective of whether they're on the backup circuits or the grid side, and still use the solar during a grid outage. So another solution would be where you've got a separate hybrid inverter like this. So that's a SunGrow. So I better cover up Smile. It's a SunGrow hybrid inverter with it's a separate from another company battery. So it's a high voltage BYD battery. It's one of the compatible batteries. So that's a DC port there. And it still requires a meter upstream to be able to see the amount of energy flow. Has 2 solar inputs for 2 arrays and a backup circuit as well. One of the catches though is people get a bit excited by this backup. They go, oh, it's great. Can't you just put the whole house on the backup circuit? You've got to check what the rating of the hybrid inverter is. And in backup mode, it's often a lot less than what it can feed to the grid when it's exporting power. So this might be, I can't remember what the SunGrow is, but the earlier models, not this new one, but the earlier models could feed 5 kilowatts to the grid, but only 2.5 kilowatts to the backup circuit when the grid failed. 2.5 kilowatts is probably not going to be my pool. Take the swimming pool out. Lighting, yes. Dishwasher, probably, but that's about it. 2.5 kilowatts isn't very much. That's basically a toaster and a kettle and you're done. So be cautious what you put on the backup circuit, or sometimes called the EPS, the essential power system circuit. Put just essential loads and light loads like lighting, maybe a fridge, not the whole kitchen.
Most of the hybrid inverters are rated at 20 amps on a backup system. Is that correct?
It does vary, but yeah, generally it's not the. Some are symmetrical, like GoodWe. The GoodWe ES is 5 kilowatts of grid feed and 5 kilowatts of backup, so it's got a symmetrical rating. But it's more common that it's a lesser in the backup mode. Yep. Okay, well, look, we've just come to the end of this session, and just a bit of a wrap up, really, so I'll just stop sharing that. People, you know, some of you have talked a lot and asked lots of questions. That's great. Some of you sat there quietly listening. If you still feel that you've got questions unanswered, I'm really happy to take them via email. You've got my email address, so feel free to fire those through to me. And those of you that wanted to have a go at designing the system, I sent through the formulas, and we did the full formulas today, and you want me to check them for you, I'm happy to do that as well. So if you've got a design you want to run past me, really happy to check it out and give you some critical feedback included. Otherwise, otherwise, you can see I have a lot of content free online as well through my channel, the Smart Energy Lab on YouTube. So if you're, bored at nighttime and you want to sit back and scroll through some YouTube's Smart Energy Lab, that's me. Mostly it will be about products that are available. And I also have a side channel called, interestingly enough, Everything Off Grid. And it's actually a bit more personal. It's about living off grid, my experience of living off grid, and some of the people that live here on the housing co-op. So it's a separate channel, everything off grid. And yeah, I interview people about their houses and how they built them and what they're made of. So yeah, that's kind of more social, less technical. Otherwise, thanks everyone for attending, and I'll be wrapping up these recordings and sending them out to you, yesterday's and today's, over the next day or so.
Thank you very much, Glenn. Thank you, everyone. Thank you.
Thanks, Glenn.
Thank you, Glenn.
All the best.
Cheers.
Thank you.
Thank you very much.
Thanks, Glenn. Thank you.
Yes.
I got away from a baby. Hello.
She's sleeping, that's why. All right.